Hi everyone, we're going to be looking at section 2.3 in our Math 203 course today. This is for Tuesday, January 23rd. We are finally going to get beyond the investigation portion of limits. We have a really good idea of how they work by looking at tables and graphs, and we're going to now look at some algebraic techniques to help us out. So the graphical and the numerical techniques that we have done for estimation has been a great way to see how this works, but it's not precise. It can lead to some incorrect results. So in this section, we want to learn analytical methods so that we can find limits precisely. Okay, so we're going to start off with some limit laws. These are pretty natural things to do. We're going to have two functions, f of x and g of x, and we're going to be looking at their limits as x approaches a. And we're going to see what happens when we add, subtract, multiply, divide, look at powers, constants, roots, etc. So first up, we can see that f and g are added together, so we have the sum. So it seems pretty natural to split that up. Okay, so that's what I'm going to call the separate rule, and that happens for both addition and subtraction. This next one is used very widely. Sometimes your function is multiplied by a constant. So when we have a constant that's multiplied, we can pull that constant out of the limit and just evaluate the limit of the function. So this is what I call the pull out the constant rule. We'll be doing this one quite a bit. Okay, and the multiply and divide here, we have the same as what happened with add and subtract, where we can separate that. All right, when we get down to the power and root, those look like the constant multiple one. So here we can go ahead and pull that out of the limit. Remember, the root is a fractional exponent. So just to give you an example, if you had something like the square root of x, you can think about that as x to the 1/2, and you can pull those powers out. Okay, so we're going to make sure that we can pull out either the power or the root. Okay, so for our first example, it's just a matter of recognizing these properties and seeing what's happening. You don't have to necessarily be truly formal with this. You are given the answers for limits. You didn't have to find them. So we have the limit as x approaches 1 of f of x is 8. The limit as x approaches 1 of g of x is 3. And the limit as x approaches 1 of h of x is 2. So we're going to use the limit laws we just looked at to justify what happens. So in this first example, we have the limit of x approaches 1 of f of x and h of x. So if we look here, this is a multiplication problem. So if we go back, we should be able to use our separate property. Okay, so I'm going to go ahead and write that. So I can make this into the limit as x approaches 1 of f of x times the limit as x approaches 1 of h of x. Okay, and it said to justify, so I'm okay if you separate if you want. You may want to tell me the operation. So something about the product rule or separate products would be fine with me. Okay, at this stage, we can go ahead and plug in the answers we're given. So 8 is the answer for that limit, and 2 is the answer for the h of x limit, so we get an overall answer of 16. Okay, and the next one we have a little bit more work. Okay, we can see a cube root, we can see a multiplication of f and g, and then we have an addition of 3. So the first thing that I would work on is dealing with this root. Okay, so just as a reminder that if you have a root, okay, so if we have a cube root of x, okay, what happens there is it's really x to the 1/3. We can think of it that way. So we are going to go ahead and pull that out. So pull out that root. Okay, so we're going to have the limit as x approaches 1. Okay, so we're going to have f of x, g of x plus 3. Okay, and then we want that whole thing to the cube root or to the 1/3 power. So I'm going to write it like that. Okay, if you put a cube root over the whole thing, that's okay as well. So we are going to pull out the root. So that would be the root rule. So next up, we have some separating that we can do. So we should be able to separate this multiplication, and then we should also be able to separate over the addition. So if I go through and do that, I'm going to have the limit as x approaches 1 of the f of x function. And then I can separate that from the limit as x approaches 1 of the g of x function. And then I also need to separate the addition, so I'm going to have the limit as x approaches 1 of 3, that constant function. And remember, all of this is to the cube root or the 1/3. So this is a separate rule, so I would say we're separating over product and sum, or if you want to say separate over multiplication and addition, that's fine too. So I'm going to be less formal here. I'm going to separate multiplication and addition. Okay. All right, at this stage, we should be ready to evaluate our limits. So we know that the limit as x approaches 1 of this guy is 8. The limit of x approaches 1 of g of x is 3. Okay, so this one, the limit of x approaches 1 of 3. Okay, so think about that. That would be a horizontal line. So it doesn't matter what value of a, whether it's 1 or something else you're approaching, you're always going to get the answer of 3. Okay, and then this is all to the 1/3 power. Okay, so the arithmetic, we are going to get 24 plus 3, so that's 27 to the 1/3 power, or the cube root of 27, which is just 3. All right, so that gives you some easy examples on how our limit property works. It really just comes down to separate over addition, subtraction, multiplication, division, and pull out any constants, powers, or roots. All right, so next up, we're going to look at some limits of some very popular functions, which are the polynomial and the rational functions. So remember that a polynomial, just to give you guys some examples, are things like lines, parabolas, cubics, etc. They're really nice. They're continuous. They don't have any breaks in the graph. They go for the whole domain of negative infinity to infinity. Rational functions are fractions of polynomials. So just to give you, you could put a line over a parabola. You just have to watch out for the denominator when it comes to fractions of polynomials. All right, so here's how you're going to evaluate the limits for these kinds. If you're dealing with a polynomial function, there's not going to be any problem. Basically, I want you to take the a value and just plug it in for x, and you can find the answer, okay? Now, for rational functions, we have to be a little bit more careful. Our goal is hopefully that we can take the a value and plug it in for the x value, but we have to make sure that we're watching that denominator. We don't want to plug in anything that will make division by 0. So basically, the best case scenario for both of these is we can directly substitute in the a value to evaluate the limit, provided that a is in the domain of the function. Okay, so rational functions, we're going to really have to watch out for that. All right, so these should be some very easy limits for us to evaluate. The first one, hopefully we recognize when we see this formula that it's a line. So this fits in the polynomial group. So it should be very easy to see what's happening. All we need to do is plug in the 1 value for x. So when you want to see where this is heading, as I approach 1, I'm going to get 3. Okay, this shouldn't be shocking for us. If we fall back on our graphs and our pictures that we were doing, this is something that should be easy for us to graph. Okay, we know it has a y value, y-intercept of 5, and then another point on the line would be the value we just found for our limit. So 1, 3. Okay, so there would be our line. Okay, so it's definitely not shocking that we got a limit of 3. With polynomials, our function value should match what we get for the limit. Okay, so we can see that from the picture. Part B is another polynomial function. So hopefully you recognize with this squared right here that we have a parabola. So we have a parabola that is going to open up because of the leading term of the squared being a positive. So this is another one where we're finding the point on the parabola and it ends up being our limit. So we just need to plug in a -2 for x and be very careful with our signs. So we have -2 squared plus 5 times -2 plus 7. Okay, and then when we evaluate, this one is 4. We're getting -10 plus 7. And then totaling this up, we get that the limit is 1. Okay, so we could do a similar thing, draw a picture of the parabola and show that our answer for the evaluation matches our picture. So those were both polynomial examples. This next one is a rational function. Okay, so one thing to kind of watch out for with rational functions is the denominator. So lucky for you guys, I didn't ask you to evaluate this as x goes to -7. If I did, we'd have a little bit more work that we needed to do. So as long as we don't look at x goes to -7, we should be able to evaluate this for anything. Okay, so I'm just going to make that note about that x can't be -7 off to the side. Reminder of future things to come here. So this is going to have the same evaluation that we've just done where we plug in -1 for x. So we're going to get -1 squared minus 5 times -1. And then in the denominator, we'll have -1 plus 7. Okay, so our denominator is a little bit easier to find. That's 6 here. This is 1 plus 5. So we really get 6 over 6, which is 1. Okay, so that would be a point on our rational function. Just as a mental note, whenever you find these issues in the denominator, if you're not able to kind of make them go away by factoring the numerator and canceling, these guys end up being vertical asymptotes, which is something we'll talk about in section 2.4. Okay, so that gives you a nice, easy introduction to limits. That's something that we're always going to try when we're evaluating limits analytically. We're going to try to take the a number at whatever x is approaching and plug that in first, and hopefully that won't lead to any problems and we'll be able to get an answer. All right, so we're going to look at this in terms of one-sided limits. We're going to try to evaluate similarly. We just have to pay attention to the domain. If I look at this function here, I get this horizontal line of 0, but this is only good for x less than or equal to -5. So break that down. So we're going to use that function as long as we're equal to -5 or left of -5. Okay, so on this next one, we want to be careful here. So we'll have this square root function. This is only good for -5 to 5, but we're between those values. Okay, so I want to look at this formula if I'm between -5 and 5. Okay. All right, breaking this down a little bit more, if I look at the different pieces. So this formula is good if I'm right of -5. Okay, and then because of the less than 5, that means I'm going to be left of 5. For some reason, my pen doesn't want to write here. There we go. Okay, so that breaks that part down. So our last piece is this x greater than or equal to 5. We're back to a line 3x. And this one is only good if we're equal to 5 and then on the right side of 5. So I'll make that note too. So equal to 5 or right of 5. Okay, so just breaking that down in words. So that's going to be important when we get to the sided limits, because we know from what we learned yesterday that a plus sign means on the right side of the number and a minus sign means we're on the left side of the number. Okay, so this first one that we're looking at, we have to decide which formula is valid, and we're looking at the left side of -5 because of that minus sign. So if I go back and I'm going to see which formula is valid for the left side of -5, okay, I see that that is given by the top formula, so you may want to kind of use a note. That's what you want to use. So if I'm plugging that into the top formula, it's pretty easy because it doesn't matter what x value you plug in, you're always going to get an answer of 0. So that's the answer for this first one. Okay. All right, so the next one, we are looking at the right side of -5. So on the right side of -5, I need to see where that is. So that looks like what we wrote for our middle formula. That's a formula that's valid for the right side. So go ahead and make that note. Okay, so that means I want to plug in -5 into my middle formula. So when I evaluate, I'm going to have 25 minus the quantity -5 squared. Okay, so working that out, I'm going to get the square root of 25 minus 25, which is going to be the square root of 0, so I get 0 there. Okay, so last here in part C, we're going to pull this together, and we're looking at the overall limit at -5. So this is going to use theorem 2.1 from yesterday. So it's not really important that we remember the number, but what we do want to remember is the gist. So we talked about if the left side and the right side have the same answer, then the overall limit has that same answer too. So this has to have an answer of 0 because of part A and B. Okay, because the left and right side of -5 both have answers of 0. Okay, we're going to do a similar thing with looking at 5. So here we're going to start off and we're going to be looking at the left side of 5. So that looks like it should be that middle formula that is giving us the left side of 5. So I'm going to put in 5 into that square root formula. So I'm going to have 25 minus 5 squared. It's going to be the square root of 25 minus 25, so I'm going to get the square root of 0 again. Okay, on the next one, I want to look at the right side of 5. So on the right side of 5, that should be this formula here, where I put equals -5, or there should be another little r in there, the right side of 5. So we're going to be using the bottom formula for this one. So if I plug this in to the bottom formula, I'm going to get 3 times 5. And that's equal to 15. Okay, so you want to use that theorem 2.1 again. So we go back and we look at our answers. This time we see that they do not go to the same place on the left and right side. So when they do not go to the same place, we say that the limit does not exist. All right, so that would be by what we just did in D and E. All right, so our last thing that we're going to look at today, and we'll save a lot of this for tomorrow, but I want to give us an introduction, is we have a lot of algebra that we've learned along the way that should help us with evaluation of limits. So far today we've been able to find most of our limits by just using direct substitution. Now we may have to do a little bit of work before we're allowed to do any kind of substitution. So there's some algebra tricks that may come into play. Factoring is a big one. Okay, so you definitely should know all your factoring rules coming into calculus. We're going to use this thing called conjugates. Okay, that's going to help us out whenever we hit problems with square roots. And then you may have to, use some trig identities. Remember, I did post a trig identity sheet in Brightspace if you need it. You may have to do other things like, find common denominators. So any of those algebra tricks of the trade could be used. Okay, so we're going to do a couple of these today just so that you can see some algebra tricks that you might want to use. So the first thing we want to recognize is that this is a rational function. It's a fraction of polynomials. And, I mentioned earlier with these, if you can plug in, great, but you have to pay attention to that denominator. So this would be a case where we are in trouble because x cannot be 2. If we tried to plug in 2, we'd get division by 0. So we cannot use direct substitution here. So we need to see if there's any algebra that we can use to try to make that go away. And the algebra that we're going to use is factoring. Factoring is going to help us out. Okay, we had one similar to this in our section 2.2 notes where we had to factor and we got a line with a hole in it. And that's what this is going to end up being as well. So you've seen the picture of this. Now we're just going to focus on the algebra. So as you're doing your algebra, you have to keep your limit notation. That's very important. So the only time that can be dropped is the minute that you evaluate. In this case, the minute that we plug 2 in. So since I'm manipulating this fraction and I'm not plugging 2 in yet, make sure that that is in front of the fraction. Okay, so I want to try to factor. Remember, with a trinomial with a leading term, you want to multiply to both of the ends, and your goal is to try to add to that middle. So it's pretty easy to multiply to 3 because we only have 3x and x as our option. Also very easy to multiply to 2 because we only have 1 times 2 as our option. Because of the plus sign here, we need to use the same side as the middle, so those will be minus. And it does matter where you put the 2 and the 1. To get the adding to -7, we're going to want the 2 here because we can see that this outside gives us -6. And then we'll want to put the 1 here. So when we add those two pieces together, we will get a -6 and a -1, which will add up to -7. Okay, now we want to eyeball our denominator. Almost looks like the x minus 2. If we go ahead and pull out a -1, it will become x minus 2. So that may be something that you want to do. Hopefully you'll start to recognize when you have like an x minus 2 over 2 minus x, it'll always cancel to -1, but we can use the greatest common factor there to kind of help us out. So the good news is our issue that we had disappears. So we have the limit as x approaches 2 of 3x minus 1 all over -1. So this would be the case where now we can go ahead and evaluate and plug in the 2. So we get 3 times 2 minus 1 all over -1. So this will be 5 over -1. So we get an answer of -5. So just as a review of the pictures, I mentioned that this would be a line with a hole in it. So the line, if you wanted to, go ahead and, divide by -1, you'd get -3x plus 1. That would be the line. So if I was drawing a picture of this, and it should match what we get for our limit, you should always find where the hole is, and that's what the limit answer gives us. So if we plug in 2, we get -5. Okay, so there would be where the hole is on the line. And then we know that we need another point on the line, and we can use the y-intercept, which is 1. Okay, so this would be what the line looks like. So if you put this in your graphing calculator, you wouldn't see the hole, but you would see an error in your table. And we can see if we did kind of the merging, right? We can see from the left side, we go right here, and then from the right side, we go, and that matches our algebra that we got with factoring, that our answer is -5. Okay, so those pictures are nice checks for you. It's how we started with chapter 2, so use that to kind of help you out if you can when you're switching to the algebraic techniques here. All right, so that's how factoring is going to work. You'll see a lot of that come up. We are going to go through a couple more examples. One I want to look at is a fraction, so part B here. With fractions, you really need to have a lowest common denominator. Okay, so I'll save part C for class tomorrow, and we'll do part B together today. One thing you might want to do in something like part B, this is a complex fraction. Remember, this middle line means divided by. So if you're dividing by h, it's the same thing as multiplying by 1 over h. So you may want to take that multiplication out of 1 over h and just do a little rewriting like this. It kind of highlights the issue for you if you do a little rewriting. So I haven't done anything to this problem. I just, use like, if I have 2/3 divided by 2, it's really 2/3 times 1/2. That's all I did. So, this doesn't look very nice, does it? Okay, so make it into something that is a little bit nicer for you guys. So I wrote it this way because I can see that h is my issue, right? I cannot plug in 0 because I get division by 0 here. I'm okay right here, right? 5 plus 0 is 5. But I need to make this h disappear. So that's my goal, is I need to make him go away, and then I'll be able to evaluate the limit. Okay, so to do this, I need to have a common denominator in the parentheses. So this 5 plus h term is going to need to be multiplied by 5. So if you multiply downstairs, make sure you multiply upstairs. And then on the other one, I'm going to raise my parenthesis to give me a little bit of room here. Maybe. Okay. Let's see here. It's not liking what I'm doing, so I'm just going to go with it here. So on this one, I need the 5 plus h. So I need to make sure I put it up and down. So. All right, so all of the work, once you have the common denominator, should be done in the numerator. So we have the limit as h goes to 0. We have 1 over h. Our common denominator is 5 times 5 plus h. So you can multiply that out if you want to, but really there's no need. In the numerator, we have 1 times 5. And then be really, really careful with this. Remember, the minus sign needs to go through the entire numerator. So we know multiplying by 1 is no big deal, okay, but we definitely want to distribute that negative sign. So you're going to have a -5 and a negative h. Okay, so the good news is here, these 5s are going to cancel out because that's 0. And then the next piece of best news is our goal was to try to get rid of this h. And we can now that the 5s are gone. So this cancels into -1, right? The h's will go away. So if we do a little rewriting, I'm going to get -1 all over. Okay, now I'm in a place where I won't get division by 0. So I can go ahead and plug in. So I'm going to get -1 all over 5. And then it's going to be just times 5 because of 5 plus 0. So my overall answer is -1 over 25. All right, so this would be the place where there would be the hole in the graph. This one would be a little bit more complicated to draw because of the complex fraction that we were given. But mentally I'm thinking that would be where the hole was at 0, and then negative 125 would be the y value. All right, so we're going to look at one last example, and this kind of brings us back to when we first started evaluating limits, which we should always try first. We should try to do the plug-in. So on parts A and B, we were not able to do that because when we plugged in, we got division by 0. But here, I think direct substitution is going to be just fine for us. So if we plug in, we are going to get 3 on the top, so no worries there. And then we're going to have 16. 3 times 0 is just going to be 0. So, and then we have this plus 4 outside of the square root. So it doesn't look like that is going to lead to division by 0. So we should be able to see where our hole in our graph is going to be. The square root of 16 is 4. So our hole would be at 0, 3/8. So I'm going to make that note since I've been mentioning. So once again, a little bit of a more complicated function here to draw, but mentally I'm thinking about, what would that picture look like if I had to do it. Okay, so that gives us a good introduction to taking care of limits analytically. We'll work the rest of the examples in class tomorrow. As always, I'll make sure that I take any questions about what you've seen on video, and you're welcome to shoot me an email as well if that works for you. Enjoy the rest of your Tuesday.